So for this series of questions, how do we work them out? So what are they saying? Saying show that each of the following differential equations is homogeneous. Then solve the equations. So we're going to do two from here. So we'll do A and C here. Okay, so what happens? Okay, so let's look at A. So the first thing we have to do, we have to check if the differential equation is homogeneous. So to do that, we must first present the differential equation in the form dy dx is equals to f of x comma y. In other words, we want to just sort out the dx and the dy so that they are presented in this form, then take everything else the other side so that they come out, they create f of x comma y. So this is what we want to do. So how are we going to do it? So well, we'll start by taking this part to the right hand side. And in this case, we'll have x plus y. And then we have dx is equal to dx dy. So this is what we end up having. And then from here, divide both sides by x. The x comes to the left side over x dx. Now divide both sides by dx so that it joins dy on the right side. Okay, so with this, we have now presented our differential equation so that everything on the dy dx is isolated on the left side, and then everything x and y is on the right side. Now this becomes our f of x comma y. So our f of x comma y has simplified to just be x plus y over x. We can now use that to check if our differential equation is homogeneous. So let's look at f of tx ty. Here, where there's x, we put tx. Where there's y, we put ty. I see x again, so we put tx there. We quickly notice that the t is present on each term. So the t here is going to cancel out. So that now f of tx comma ty reduces to just x plus y over plus y over x. And notice that this is the same as the function we started with earlier, which is just f of x comma y. So because of this realization or that observation, we conclude that our differential equation is actually homogeneous. Now, seeing that our differential equation is homogeneous, how do we work it out? Well, to solve a differential equation, it follows that then one of its solutions has this form, or y is equals to vx is actually also a solution to our differential equation. Here, want to keep in mind that v is actually a function of x. So this is a function of x. So from here, you can then find dy dx. Why do we need dy dx? Because it's what we're going to place where we have dy dx in the differential equation. So let's differentiate this solution once. Since v is a function of x, we have to differentiate by product rule there. We'll keep v constant, differentiate x, which will just be v, plus, now we'll keep x and differentiate v. So we now have an expression for dy dx. So you don't always have to show that you're differentiating by product rule here. If you can remember this equation and this equation for a differential equation which is homogeneous, you can just drop them and use them to solve the differential equation. So with that in mind, let's proceed to now the substitution. Where there's dy dx, I'll put this And then on the right side, where there's x, x will maintain. But where there's y, we are substituting vx. And then we see in the denominator what we have, that's x, so it will remain exactly the way it is. So our expression has reduced to this. And what happens here? This part here, we can write them as separate fractions. So we'll have x dv dx equal to, this will be x over x, which will be 1, plus vx over x. This will remain or reduce to just v. So you can say x is present everywhere, so that you remain with just 1 plus v on the right side. The v on the left and the v on the right will subtract out, so that now we have x dv dx is equals to 1. Now, the argument or the idea of solving homogeneous equations here is that once you make the substitution, the resulting solution or the resulting problem will actually be a function or an equation still differential, but that you can now easily solve by separation of variables. As you can see here, just cross multiply the dx so that it goes on the right side. Divide both sides by x so that now you have 1 over x on the right dx. And from here, you can now integrate both sides so that you have the integral of 1 over x dx on the right. Finally, when you integrate, 1 over x, that will reduce to just ln x. Since we're done integrating, we introduce the constant c there. After finding the solution to what v is, you now come back to this expression. Y is equal to vx. Remember, this was how we defined y. So from here, v is here. There are two ways you can proceed with this. Since our solution has to be y is equals to something, in this case, I can get my expression for v and plug it here so that I have my so that now I have y is equal to x will be outside, and then where there's v, I'll put ln x plus c. So that now y will be equals to x ln x plus xc. So this becomes my solution. We can present it this way. Or in some cases, you find that from here, v will be made the subject of the formula, so that v will be equals to y over x. Then get the y over x now and substitute it here where you have v, so that now you will have y over x is equals to the solution for v here, which was ln x plus c. You see that in this case as well, we still reduce to x ln x plus xc as our solution. So this is how we solve homogeneous differential equations. Now we move on to a tricky one. So now we move on to this problem here. So how do we solve this? Still, we want to first check if it is homogeneous, then move on to solve the expression. Okay, so here, how do we work out this problem? So just like before, we first want to check if it is homogeneous. So to do that, we'll isolate dy on the right side, and this becomes 6x squared 4xy dy. Then now we'll take the dx to join dy and take this to join this expression on the left. Then I'll just rearrange so that I start with my dy dx. Then I'll have 3x squared 9xy plus 5y squared over 6x squared plus 4xy. So this is what we have now. So here, clearly, our f of x comma y is equal to this expression. And we can now check what f of t x comma ty would be. So where there's x, we'll put tx. This has to be squared. Here, we'll put tx. Now we see y, so where there's y, we'll put ty. And then again, we see y, ty. But this y is squared. The denominator, we have 6x squared, so where there's x, we'll put tx. It has to be squared. We see x, so tx. We see y, ty. Now we simplify. This will be 3t squared, x squared, 9, t squared, x, y, t squared because you have this t here and that t, plus 5t squared, y squared. In the denominator, you have 6t squared, x squared, plus 4t squared, x and y. So this is where we are now. And when you observe, you see that t squared can be factored out from all the terms in the numerator. And if you did that, you remain with 3x squared, 9xy, 5y squared. We can do the same thing in the denominator. T squared is present. Now we have 6x squared plus 4y squared. And not y squared, just y. xy, I mean. So here, t squared and t squared would cancel. So that now our f of t x comma ty has reduced to this. And notice that this is what was our f of x comma y. Based on this, we conclude that our differential equation is homogeneous. And if it is homogeneous, let's move on to solving it. And here, for homogeneous differential equations, we, as we pointed out, know that this is a solution. And dy dx will reduce to v plus x dv dx. So this is what we have. So we're going to get these two and substitute them in this expression. Because remember, even though I have my, even though I'm writing this was for f of t, x, ty, we know to say it's the same as that one. So I'll be substituting in this expression. You only proceed to the substitution if you actually concluded that the differential equation is homogeneous. So where there is dy dx, we'll put v plus x dv dx. On the right side, we have 3x squared, 9x, where there's y, we're putting vx, plus 5, we see y coming in, so vx, but this one has to be squared. In the denominator, we have 6x squared, 4x, again we have y, so we put vx there as well. Let's focus on the right hand side for now. Here we'll have 3x squared plus 9x squared v plus 5 v squared x squared. And in the denominator, 6x squared remains the same. But here we now have 4x squared v. Something will cancel here. And we see that in this case, the x squared is present on all the terms in the numerator. It's also present on all the terms in the denominator. This is the only reason why we can cancel it. You can still go ahead and factor it out first and then cancel. But as long as you can see it, you can move on from there. We remain with 3 plus 9v plus 5v squared over 6 plus 4v. So this is what our v plus x dv dx is now equal to. Now, here, the easiest approach to solving this, since you already have the dv dx this side, the easiest way to solve this, get the v and take it to the right side. That's the best step you can try. You can always try when you reach this stage. When we take the v to the right side, what are we going to end up with? We'll have 3 plus 9v plus 5v squared over 6 plus 4v, but then we have minus v, this v we just joined on the right. Here, we now focus on the right-hand side for now. When we make it a single fraction, just the right-hand side, this will be minus v. Here we'll have to multiply 6 and 4v, so that everything can now be written with a common denominator. The right-hand side, the left-hand side will remain the same. Few terms are going to simplify here. When you distribute the minus v, it will also be minus 4v. When we simplify, the 9v will simplify with the 6v. The 5v squared will simplify with this one here. When it multiplied with this, it became 4v squared. We missed that square, but then we saw it. Ended up seeing it. Okay, so now we're saying the 5v squared will simplify with the minus 4v squared there, so that we have plus v squared over 6 plus 4v. So this is what we now have, dv dx. And as I pointed out, whenever you're utilizing this technique, after substituting y is equals to vx and its derivative, after simplifying, the resulting expression must be an expression you can solve using separation of variables. And here, this is such a one. To do that, this must all come to the left side. How will it go? Cross multiply. The 6 plus 4v will multiply up here. Down here, we'll have the 3 plus 3v plus v squared. It will multiply downwards, while the dx will multiply up. We still have the dv here. The dx will multiply up, and the x will come down. So I can still do it slowly, but I hope you were able to follow up to here. Do you have anyone who would want to see how that comes up, or we were able to follow? Okay, looks like we're good. So guys, if I take a shortcut like the way I took this one, feel free to take me back. I'll always be happy to explain to it. Once you have managed to reach this stage, notice that you've isolated everything with a v on the left side paired with dv, everything with an x on the right side paired with dx. Here, we can now integrate. the right hand side is easy, and you can see that the integral of 1 over x is ln x. We put the modulus there because we don't want our ln to take a negative argument. We just want it to take positive arguments. But by what method can we integrate on the right side? So try to observe that. By what method can we integrate? So here we will use u substitution. So we'll just focus on the right hand side for now, left I mean, and we want to perform the integral so that we continue the problem. So if we just take it up with our right, I keep going right, our left hand side, we'll say let u be equal to 3 plus 3v plus v squared. Here, when we get du dv, we get 0 here, 3 here, and 2v here. We make du, want dv. So we make dv the subject. This will be du over 3 plus 2v. Now we can make the substitution in our expression. Where we have the denominator, we put u, because we said let that denominator be u. But while there's dv, we'll put the derivative we get from differentiating u. Here, we observe that the numerator can be simplified by factoring out 2. If we factored out 2 from the numerator, would remain with 3 where there's 6, remain with 2 where there's 4. So that now it is clear that something is going to cancel. This whole lot will go with this whole lot. So that our integral has reduced to just the integral of 1 over u du. And when we perform the integral here, we get 2 ln u as our solution. But remember what u is. U is 3 plus 3v plus v squared. So that now our integral here for the left hand side reduces to 2 ln. As long as v is not negative, this is always going to be positive, but still we'll not risk it to put the modulus there. We don't want the ln to come and complain that we gave it a negative, so we'll put a modulus. Okay, now that we have the integral on the left hand side, the solution for that integral, after integrating, it will reduce to this. Already at this stage, you observe that we can easily say that here plus a constant c. In fact, we can even try to be smart about this. We see that we have a ln here, a ln here. We can choose. This is a constant, but it's not clear what constant it is. So I can choose this constant to be in form of ln as well, so that it joins the phrase. So I can choose it to also be in form of a log. So say this is some constant, let's say ln c. So that now we can simplify this a little bit. The right hand side will now just be, because you have ln plus ln, same base, we just multiply the arguments there. So this will be ln x multiplying c. The left hand side, the 2 can go up. Remember, there's that property of natural logs where if you have ln, let's say x to the power n, this is the same as n multiplying the same expression. This power can be taken down there. So using that technique, we can argue that this can become a power here. So that now we can write it as ln. Since that is going to be squared, when the 2 goes up, I can stop worrying about it ever being negative, because that power is going to deal with it if it ever becomes negative. That v there does not have a square. Squared there is equals to ln xc. From here, we can now take the anti-ln on both sides, and if we did that, the ln would be sorted out, so that now we have 3 plus 3v plus v squared, this c squared is equals to xc. So this becomes our expression for v. We don't have something perfect to say that this is our v is equals to that. It looks like those expressions are connected. We have an implicit function of v in terms of x. So we're unable to separate them. So I think I can start just erasing this part here and writing below. Okay, so we now have this expression. But remember, this is not what we're looking for. What we're looking for is an expression for y and x. V only showed up so that we are able to use separation of variables. But now that we are done with the integral and solving the differential equation, we can now recall that we did say y was equals to vx. This implies that v is actually just equal to y over x. You see that now I am choosing to use this version because it's not possible for me to make v the subject of the formula here and substitute it where I have v. Because of that, I'll instead make v the subject of the formula here and substitute it wherever there's v in the first equation there. So now I have 3 plus 3 where there's v, y over x. There's v there again, so this will be y squared over x squared. But this has to be squared, is equals to xc. So this becomes our expression. Again, you can still square this, expand a little bit, but we'll leave it here. There was a continuation in the problem. There was a continuation. So if you check the problem, what else did they say? They said something. They said y2 is equal to negative 6. What is this? So they're saying that we know this is y a function of x. Our solution is y a function of x is equals to something. Even though we are struggling to make y the subject of the formula, as an implicit function, we're saying this is possible. It's possible for us to write y is equals to that. We just don't know how to. Now, with this in mind, they're saying that, okay, for this same thing, we're saying it is possible, we just don't know how to. If you could ever write it like that, and then plug in a 2 where there is x, it turns out that the solution or the value of y would actually be negative 6. What are they telling us? They're saying that, okay, when x is 2, y is minus 6. And what is this going to help us achieve? This will allow us to find what the constant there is. Our expression led us into some weird expression. Weird solution. Where's that weird solution? Right here. But with the condition they are given, it allows us to figure out what the constant here is. So they will always, if they want you to know what the constant is, If they don't want you to have a c present here, they'll give you a constant. They'll either give you a boundary value condition, or so that it changes to a boundary value problem, or they'll give you an initial value, and they'll tell you what y was, what x was. They'll tell you what y was when x is equals to 0. They'll say y was equals to 0. So they'll give you the initial state of the problem. So based on that, since they have told us that when x is 2, y is minus 6, so where there is x, we'll put 2. Where there's y, we'll put minus 6. Then I have minus 6 here being squared over 2 here being squared, and everything here being squared. On the right side, we have just 2 multiplying c. We see that only c here is the unknown, so finding it really shouldn't be a problem. I'll simplify this a little bit before leaving it for you. This will be 6 over 6, which is just 1, but we'll have that minus, so I'll leave it as minus here. And then plus, that will be 36 over 4, so that will be 9. So you can correct me if I've made a mistake there. But that's 36 divided by 2. That will give us 18. 18 divided by 2 will give us 9. Okay, so here the difference will be 2. 2 plus 9, that will be 11. So we now have 11 squared equals to 2c. So that we're saying that c is actually equals to 11 squared over 2. Okay, so the 11, of course, will be 121 over 2. What does this imply? It now means that our solution here, there's no need for us to now keep the c. Using the condition they gave us, we were able to find what c is. So that now, in place of c, we'll put 121 over 2. Over 2. So, because we are lazy, we'll leave our expression in this form. Okay, yeah, on this part here, since x is 2, x is down. So x is down here. Where there's x, this is where we're putting 2. And then y is on top. So here, this is where we're putting that minus 6. So yeah, just a matter of substitution there, but really everything else should be okay. So now we have minus 18 divided by 2, giving us minus 9. So that this one here is minus 9 instead, not that one. So the minus 9 and the 3, and minus 9 and the 9 will give us a 0, leaving us with only a 3 this side, a 3 being squared. When we square the 3, we'll get back 9. So that now we will have 9 over 2. So with 9 over 2, now when it comes here, where there is c, we're putting 9 over 2. Okay, so yeah, this is how it simplifies. Is there anything else? Anything else that you guys maybe observed as we are working it out? Just with the numbers, I think, yeah, when you do this for some time, it's easy to make mistakes. So just be very careful. Here we're just discussing. It's okay when you make mistakes, we can see them together and correct them. But in the test, just take your time. Don't make unnecessary mistakes.